important section though. Section 4.5 is the normal distribution is sort of the basis for all the statistics we do. And so this is, we'll go through this kind of quickly and we'll spend a lot of time in class on it. But it's, a really, really common distribution. It's a continuous distribution, unlike the binomial and Poisson distributions. It's for continuous variables, and it's really common for any measurement. So like almost any measurement, like from the distance from your nose to your lip. If we looked at all those different values for like all the people in our class, they'd probably stack up in this shape, okay? Or if you went and measured like the diameter of every oak tree on campus or whatever, okay? So also errors are always normally distributed. So lots of things in the world are normally distributed, all right? You might recall that we used to always have to do integrals for probability to like calculate probabilities for continuous random variables. And you'll see in this slide, they show you the probability density function f of x, like you'd have to integrate that. Here's the thing, you don't have to here. All right, the normal distribution is so common that they give you tables, like we're going to use a table to calculate these areas under the curve. And or you could use technology to do it like Microsoft Excel or Google Sheets or R. We'll be using that later. Most Python would have normal distribution stuff in it. All right, really all you need to know. So no integration required. Sweet. What you need to know to be able to do things with a normal distribution is you have to know their mean, like the variables mean and variance, okay, or mean and standard deviation. So if you know like x is the diameter of a tree, right, of a certain kind of tree, and you wanted to calculate things about that, probabilities about that, you'd have to know the mean diameter and you have to know the variance for diameter. The other thing you need to know is so we know we have to know the mean and the standard deviation or the variance, right? The other thing you need to know is that, there was this function, right? If you graph that function, that really ugly function that I showed you that we crossed out, it ends up being, that's not perfect, okay? But it ends up being this bell-shaped curve. So have you ever heard about a bell curve or a normal curve or a Gaussian curve? That's what we're talking about. And it should be, this is supposed to be symmetric. So when you draw yours symmetric. It's hard to do with a stylus. All right. And the things that you need to know is that the mean is right in the middle. All right. And then the standard deviation is something about spread, right? How spread out things are. There are about 3 standard deviations on each side of that. I have to make them smaller on this side. But if you went by standard deviations, right, this would be the mean plus 1 standard deviation, the mean plus 2 standard deviations, the mean plus 3 standard deviations, right, minus 1 standard deviation, minus 2 standard deviations, the mean minus 3 standard deviations, then you've got about everyone. That's what you need to know, all right? So you need to know what this thing looks like. You need to know that about 6 standard deviations gives you about everyone. We're going to see another slide about that in just a second. Yeah, and in fact, this is a really, really common kind of rule of thumb that people use, okay, for normal distribution. The 68, 95, I call it the 68, 95, 100% rule. They call it the 99.7% rule. But you'll see within 1 standard deviation of the mean, right, if you just go 1, out 1, and here's the mean. If you go out a standard deviation to the right and down, you get about 68% of the distribution. If you go 2, you got about 95. So notice, even just 2 standard deviations away from the mean, you've got almost everyone, 95. All right. So that's just to try to like tell you how much like we know about the normal distribution. Once you know something about measurements, you know so much about how things are distributed. Depending on what we're measuring, we won't know, we'll have them, there'll be lots of different means. Like think about if you did the diameters of oak trees or the diameters of maple trees or elm trees or whatever kinds of ginkgo trees, right? They're going to have totally different means and standard deviations, right? So there's like infinitely many different normal distributions that are possible. So we have to have these standard units. You'll see that we're going to call these Z's, okay? And these standard units, kind of like using Celsius instead of Fahrenheit, right? Fahrenheit is kind of weird, but Celsius does a nice thing and just makes like 0 freezing, right? The standard normal, okay, they call it standard units, but I call it standard normal, okay? The nice thing is the mean is 0, just makes the mean 0 and the standard deviation 1. So this is the standard by which we're going to measure everything. So when you look at a table, it's always going to be standard normal. So let's look at a real quick example. So let's say we have I don't know. Let's say we have IQ scores are a really common example to use for normal distribution. You guys probably didn't have your IQs taken ever. You may have done it online, which is not real IQ scores. But when I was a kid and your parents were kids, we had to have our IQs measured, which was ridiculous. I can go on and on about that, but I won't. All right. So IQ scores and all standardized test scores are normally distributed, okay? And that's what standardized test means. It means they know it's normally distributed before you take the test. All right, so we know there's 3 standard deviations on each side. They're going by 16s, right? So these are the geniuses, 148. Not very many. So when you take your IQ, when you do your IQ online and they tell you have 148, probably don't. All right. And neither do I. Not just you. Anyone. Not very many people, right? Because there's not very many people beyond 2 standard deviations. All right. So we could fill all these out. Here's how standard normal works. It just makes a new measuring stick. So if these were x's, I'll usually just call whatever the original distribution with its mean and standard deviation, which you call them mean sub x and standard deviation sub x, right? Those are those, but now z will just be, it'll make 100 0, it'll make 116 1, it'll make this 2, this 3, and then nice. Below the mean are negative numbers. So it's a really nice system. It tells you a lot, right? Kind of how you would want it. It's actually how many standard deviations. So Z gives the number of standard deviations from the mean. So Z-scores are kind of nice that way. So we're going to practice just how you're going to use this to do calculations here in a second. The conversion formula from going from an X, right, the original distribution, to the Z is just this. All right, so that's something you need to know. All right, so that gives you a Z-score. So you take the original value. I call this the score. I'll just say these words usually. The score minus the mean over the standard deviation. I'll usually say it in those words. Standard deviation. Sorry, can't write an S. All right, but the score minus the mean over the standard deviation. So, like if you had an IQ of 148, you take 148 minus the mean, that'll give you 48, divided by 16, that would give you 3 for your Z-score. 3 standard deviations above the mean, right? Okay. All right, so like for example, if we wanted to do, like if we had aluminum sheets, big engineering example, aluminum sheets used to make beverage cans have a thickness in thousandths of an inch that are normally distributed. So we know we have normal, we know the mean is 10, we know the standard deviation is 1.3. particular sheet is 10.8 thousandths of an inch. Notice that's above the mean. It should be a positive z-score. So z would be the score, 10.8. So x was 10.8. 10.8 minus 10 over 1.3. So whatever we get, it'll be something less than 1, right? 0.8 over 1.3, whatever that is. All right, so calculate that. I want to see that in your prep work. Do the calculation, give me a little box around it, and I'll look for that. Similarly, we can go backwards. So the thickness of a certain sheet has a z-score of negative 1.7. So now we know z is negative 1.7. And we want to know the thickness of the sheet in original units of thousands of inches. So we want to know what the x is. So in your prep work, solve for x. So figure out what the original was. So you can go backwards, in other words, right? Put it in a box so I can see it in your prep work. So I already told you that we're not going to have to do integrals, right? No integrals. Woohoo! Right? Didn't go so well for some of you anyway, right? But you don't have to do them for this section. All right? We have this table in our book, table 8.2, that gives you a standard normal table. Just for the standard normal, mean 0, right? Mean 0, standard deviation 1 for z. All right? And also it's in the inside front cover of your book. We can convert any normal into a standard normal, so we can always compute areas. And this always gives the left-hand tail of the curve, which is a capital F. Okay, so it's a capital F for these z's. Remember, that's a less than or equal to probability. We've been working on that. We've been practicing that with the binomial and the Poisson, so you should be used to it. So you're going to have to do a little problem solving. Don't rely on a formula for these. Problem solve it. Think it out. It's way easier, and it'll apply to anything then. Let's look at an example. All right, so this first one, find the area under the normal curve to the left of, and this should be standard normal curve, to the left of z equals 0.47. I would draw a picture. It doesn't have to be a good picture. Look how lovely that is, right? So we know that 0 is in the middle, so 0.47, that's not a probability, not a probability. It's one of these values on this axis, 0.47. And we want area to the left. All right, look at the book. Look in the inside front cover of your book right now. You can even pause the video. Notice that this picture looks like the inside front cover of your book picture, which means it's ideal. This is an easy problem. This is like a gimme, right? So what you have to do is you have to look in the table. You look in the 0 column, all right, so or 0 row, so go to z equals, right, so go to 0.0 row, positive 0.0 on the right-hand page, and then go over, actually 0.4, my bad, right, 0.4 row, and then go to the 0.07 column, right, so find that spot, and you will find an area, a number, and that's the area under the curve. Notice it should be more than 0.5, right? We know the total area is 1. So this area should be bigger than 0.5, and it is. It's 0.6808. So that's the probability of being to the left of this value. That's the probability. All right.